Welcome to This Explainer. Today we're going to completely change the way you look up at the night sky. We're going to demystify exactly how these massive objects actually manage to stay up in space, uncover the sheer engineering genius behind it all, and right out of the gate, we're going to bust a very persistent myth about space travel. Let's dive in.
So why don't satellites fall out of the sky? It's a beautifully simple question, right? I mean, we've all looked up at the stars, spotted a satellite just blinking as it tracks across the darkness, and wondered, why don't these massive, multi-ton metal objects just crash straight down onto our heads? Common sense tells us what goes up must come down. So what exactly is holding them up there? Well, the answer isn't magic, and it certainly isn't a lack of gravity. Okay, to really wrap our heads around this, let's start with a classic thought experiment. Just imagine throwing a baseball. If you toss it gently, it lands just a few meters away, right? If you throw it way harder, it travels a lot farther before finally hitting the dirt. Now, imagine throwing that ball so incredibly fast that as it falls downward toward the ground, the surface of the Earth actually curves away beneath it at the exact same rate. The ball literally never reaches the ground. Instead, it just keeps falling forever. And that, fundamentally, is what an orbit actually is.
So this brings us to Section 1, falling around the Earth. Grasping this concept changes absolutely everything about how we perceive spaceflight. See, there's this huge misconception out there that satellites and astronauts just float because there's zero gravity in space. But just look at the numbers. Gravity at the Earth's surface pulls you down at 9.81 meters per second squared. Up at the International Space Station, which is roughly 400 kilometers high, gravity is still pulling at about 8.7 meters per second squared. It is almost as strong up there as it is right here standing on the ground.
So why on Earth do we constantly see astronauts doing backflips and just floating around their cabins? Well, they appear weightless not because gravity pulled a disappearing act, but because both they and the spacecraft they're inside are continuously falling together at a tremendous speed. Because they're falling at the exact same rate as their environment, they experience what we call apparent weightlessness. Honestly, it's just an endless, sideways freefall.
And this incredibly delicate balance brings us to the core of our explainer today: orbit dynamics. This is the foundational branch of engineering and physics that studies exactly how objects move under the influence of gravity. It is the absolute backbone of all modern spaceflight. It's what allows engineers to answer critical questions like, hey, where will this satellite be in 10 minutes? Or are these two satellites going to crash into each other? And most importantly, it allows us to mathematically predict a spacecraft's exact location tomorrow, next week, or even years down the line.
Moving on to Section 2. Speed shapes the orbit. You see, speed entirely dictates a satellite's destiny. You literally cannot just put a satellite at a certain height and leave it hanging there. Let's step through this, because a relatively tiny change in velocity creates a dramatically different outcome. If you launch a satellite too slow, gravity wins. It falls right back to Earth. But hit a speed of roughly 7.8 kilometers per second, and boom, you achieve a beautiful circular low Earth orbit. Push it just a little bit faster, and that circle stretches out into a long ellipse. Finally, if you accelerate all the way up to 11.2 kilometers per second, you hit escape velocity, breaking free of Earth's gravity completely, to go explore the wider solar system. And this is exactly why spacecraft carry propulsion systems in the first place, to make these critical, razor-sharp adjustments to their speed.
So, the real crucial point here is that in the world of orbit dynamics, a satellite's motion at any given instant boils down to just two things: where it is, its position, and how fast and in what direction it's moving, its velocity. Together, engineers call these the state vector. If you know a satellite's current state vector, and you understand the forces acting on it, you can mathematically unroll its entire future path. It's like having a crystal ball for space.
But of course, it's never quite that easy. Section 3. Why orbits are complicated. If it were just Earth's gravity pulling on a perfectly spherical planet, predicting an orbit would be an absolute breeze. But, nature rarely makes things that simple. In reality, engineers are essentially fighting a multi-front war against these tiny invisible forces. First off, Earth isn't perfectly round. It's actually a bit lumpy, which pulls on satellites unevenly. Then you've got atmospheric drag slightly slowing things down, the actual physical pressure from solar radiation pushing against the spacecraft, and the gravitational tug of war from both the moon and the sun. Oh, and for high-precision navigation, they literally have to factor in Einstein's relativistic effects. Each of these perturbing forces introduces tiny little changes that build up over time, meaning modern software has to constantly crunch all these variables just to keep our satellites exactly where they belong.
Which leads us to Section 4, where satellites actually live.
When you factor in all that incredibly complex math, we can actually categorize our whole orbital zoo into distinct operating zones. Closest to home, we have low Earth orbit, or LEO, sitting between 160 and 2,000 kilometers up. This is the busy neighborhood where the International Space Station and those Starlink satellites live, offering high-resolution imaging and super low communication delays. Further out, we hit medium Earth orbit. This is the absolute sweet spot for GPS and navigation satellites because of its highly stable geometry. Then, way out, at 35,786 kilometers, we find geostationary orbit, or GEO. At this very specific distance, a satellite's orbit perfectly matches the Earth's 24-hour rotation. So, to us down on the ground, a weather or TV satellite in GEO appears completely fixed in the exact same spot in the sky. And finally, we have a really specialized near-polar route called a sun-synchronous orbit, or SSO. This ensures a satellite always passes over the ground at the exact same local solar time, guaranteeing perfectly consistent lighting for taking photos.
All right, Section 5, designing a real mission.
Let's ground all this fascinating physics in reality for a second and see how an engineering team actually uses orbit dynamics to solve a highly practical problem. Imagine you're part of a team tasked with designing a brand new satellite mission to monitor devastating bushfires across Australia. You've got some really strict requirements here. You need to image the entire Australian continent every 2 days. The satellite has to survive for at least 5 years. It's got to use minimal fuel. And crucially, you need consistent lighting conditions so the photos from day 1 can be accurately compared to the photos from day 500. So where exactly do you park this million-dollar machine?
Well, you certainly don't just guess. Engineers fire up their orbit dynamics software and run hundreds, maybe thousands of complex mathematical simulations. They test out low Earth orbits, they try medium Earth orbits, constantly checking ground coverage and revisit times against their fuel budgets. Ultimately, the math points them to the absolute perfect balance, a sun-synchronous orbit at approximately 600 kilometers altitude. It delivers the coverage, it saves the fuel, and it provides that absolutely crucial, consistent solar lighting. This is how orbit dynamics transforms theoretical physics into very concrete engineering decisions.
And you know, the math doesn't just stop once the rocket launches. Orbit dynamics actually governs the entire lifespan of that mission. It dictates the occasional thruster fires for what they call station keeping to fight off all those perturbing forces we talked about earlier. Space surveillance systems use it to constantly predict trajectories and actively dodge dangerous space debris. And finally, when the satellite reaches the end of its life, Orbit Dynamics estimates exactly when and where it'll safely burn up and re-enter Earth's atmosphere. The whole shebang.
I want to leave you with this final, absolutely critical takeaway from our source material today because it completely reframes how we should view spaceflight. A satellite is not floating in space. It is continuously falling around the Earth, and Orbit Dynamics tells us exactly how that journey unfolds.
It's just a breathtaking balancing act of velocity and gravity, all managed by brilliant engineering. So here's my question for you. The next time you step outside, look up into the dark and spot a tiny point of light silently tracking across the stars. Ask yourself, what invisible mathematical forces are working at that very second, fighting off the drag of the atmosphere and the pull of the moon just to keep that machine perfectly balanced in its endless continuous fall. Thanks so much for joining me on this explainer, and keep looking up.